In this video, we present the paper Dynamic and Versatile Humanoid Walking via Embedding 3D Actuated Sleep Model with Hybrid Leap-based Stepping, in which we present a computational efficient approach to realize dynamic walking on humanoids with varying center mass height through reduced order models. A canonical way of realizing humanoid walking is a zero-moment point approach with a linear inverted pendulum model. It can be viewed as embedding the walking of the leap model in the full-order dynamics of the humanoid. This approach has been realized walking on a lot of humanoids, for instance, the walking of Asimo and Shaft. The linear dynamics can be utilized for fast online planning. However, the assumption of this constant center mass height makes the walking relatively conservative. One approach to relax the center mass dynamics is embedding of the spring-loaded inverted pendulum model, sleep model, on the robot. The approach has been explored in the literature to generate dynamic walking and running on humanoids in simulation. In our previous work, we also explored this idea by using trajectory optimization to generate the walking behavior. The sleep can generate a dynamic center mass, and the resultant walking and running are visually natural looking. However, the nonlinear dynamics can challenge the planning, and the planning are typically computationally complex. Thus, the goal of this paper is to provide a computation-efficient approach to realize the dynamic walking with sleep embedding. The approach we are taking is using stepping or foot placement in a different term. The stepping approach is commonly used in the literature. The earliest example can be seen on the Robert Harper in the 80s. The capture point is a different way of stepping to achieve the desired behavior. In our previous work, we also synthesized a stepping controller based on the hybrid leap model to realize periodic walking on the underactuated robot chassis. The approach taken in this paper is an extension of our previous work. In this paper, we present a step-to-step dynamics formulation for stepping synthesis. We also analyze the performance of the stepping via a disturbance environment set. 3D and periodic walking behaviors are realized on the A-sleep model. Before we explain the stepping controller, we need to emphasize that the sleep model we use is an actuated version of the canonical sleep model. The actuation is realized by changing the uncompressed leg length. Mathematically, we can see it from its dynamics in polar coordinates. L double dot is the actuation. Here are two examples of the walking behaviors. The leg length actuation has been used in our previous publication, including the realized jumping on the bipedal robot chassis. It has also appeared in the literature for a while. Comparing to the canonical sleep model, the leg length actuation serves as energy injection. The damping of the spring dissipates energy, which together can ease the generation of versatile walking behaviors. Now we can explain the stepping controller via the step-to-step dynamics. Assuming an existing walking behavior of the A-sleep, we can define a surface in its state space where the swing foot strikes the ground. Q and DQ are the states of the A-sleep. If we investigate the evolution of the state at the pre-impact surface, we get the discrete dynamics of the walking, which is often referred as the return map in the literature. This indicates the state of the next step is influenced by the state of the current step, the step size, and the leg length actuation over the step. Assuming the leg length repeats a periodical trajectory, the walking behavior can be roughly described by the horizontal state of the system, the horizontal position, and the horizontal velocity of the walking. As a result, we have the step-to-step dynamics of the horizontal states written in this way. Figuratively, it's illustrated as this. The current step size affects the discrete dynamics of next step. The starting controller is then about how to synthesize U, the step size, to realize the desired walking behavior. The step-to-step dynamics is a highly nonlinear function. Thus, we consider approximating the nonlinear dynamics by the linear step-to-step dynamics of the hybrid leap model. The step-to-step dynamics of the A-sleep is then written in this way, where W is the dynamics difference between the two models. If we define the IROS state to be the difference between the states of the two models and apply the step size controller, where U H leap is the step size of the H leap and K is the feedback gain. This yields the aerodynamics like this, where ACL is a closed loop dynamics and W is treated as disturbance. Assuming the periodical execution of walking, W is bounded, and if ACL is stable, then there exists a disturbance invariant set of the system. The set under the dynamics is invariant. In other words, if the error starts in the set, it will stay in the set. As a result, we design nominal walking behaviors on the H leap, and then apply this hybrid leap-based stepping on the A-sleep model to generate similar behaviors. The difference between the A-sleep and the H-sleep is bounded by the set E. Note that this approach is different than linearizing the linear dynamics at a fixed point. It is about approximating the nonlinear dynamics by a linear system over a range of the state space. Additionally, a lot of linear controller can be used. For example, the linear quadratic regulator, diabetic controller, or model predictive control can be used to realize the feedback gain K, as long as the closed loop matrix ACL is stable. Here we add some details about the hybrid leap model. To the best of our knowledge, this leap model first appeared in 2002 by Kajita. It also appeared in some literature afterwards. In our previous paper, we formulated this model in more detail. The walking dynamics is composed by two parts. In the single support phase, the dynamics is a passive leap model. In the double support phase, the velocity is constant. The transition between two domains have no velocity jumps. The domain durations are assumed to be constant. As a result, we can derive the step-to-step dynamics in closed form, which is a linear dynamic system. One should note that the H leap is used to approximate the walking. The walking itself does not have to be of constant center of mass height. The double support velocity will not need to be constant. Those will produce the model difference. Once we generate the walking behavior of the A sleep, we extract the center of mass trajectory and the swing foot location, and then control the center of mass and the swing foot of the humanoid to follow those trajectories. This is realized by the task space controller. Additionally, we want the ground reaction forces to behave similarly to that of the A sleep. Thus, we apply the contact force embedding, which was proposed in our previous paper. What it does is to make sure that the actual ground normal forces is in the range of the ground normal force of the A sleep. This ensures smooth transition between the domains. Finally, we quickly summarize the approach. First, we design the desired behavior on the H leap. We start the A sleep from a stepping place motion and then use the H leap-based stepping to perturb the walking of the A sleep. This drives the difference between the A sleep and the H leap to be in an environment set E. Then we embedding the walking of the A sleep on the humanoid based on the center of mass trajectory, step, location, and the ground normal forces. Now we show some results. We first demonstrate the approach on generating a periodical walking from a static configuration. The black are the orbits of the H leap. in the sagittal and the lateral plane. The blue are the trajectory of the A slip. We can see that the A slip converges closely to the periodic walking of the H slip. So is the humanoid atlas. Here we show additional periodic walking behaviors, including walking to the lateral direction and the backward direction, and a forward walking with varying velocities. The vertical behavior of the center of mass can be adjusted by changing the initial stepping place walking of the A slip. Here we show the periodic walking with a larger center of mass height variation. The H loop can also realize non-periodic walking. The linear dynamics makes the planning to be fast, solvable quadratic programs. Here we show an example of walking to a target location. You can see that the H loop follows a similar walking of the H loop, and so is a robot. Finally, we show another example of path tracking. The planning on the H-lib is same to the previous example of using quadratic program. The difference here is we enable turning on the robot. We also did a verification here. The evolution of the error state are indicated by the black dots. The environment set E is also numerically approximated by the blue transparent polytopes. You can see that the errors are inside the environment set, which validates our method. To conclude, we present a computation-efficient approach for humanoid walking with varying center of mass height. A step-to-step dynamics formulation is proposed to synthesize stepping controller, and the H-leap model is used as the approximation. The future work will be on the understanding of the influence of the A-sleep parameter on the disturbance environment set. We are also working on realizing dynamic walking over rough terrain. Finally, we would like to thank our funding agency and also the valuable comments from the reviewers.